Okay, good morning all. From last lecture, we have started the heat treatment of the steels, and in the previous lecture, we have discussed related to the concept of the heat treatment. What is the how exactly heat treatment is conducted, and what are the objectives of the heat treatments, and then different steps which are involved in that heat treatment process. Then now here we are going to discuss the means in your syllabus heat treatments related to the steels are there only. Then for that, first, for understanding each and every heat treatment process, you should understand the transformation products of the austenite. Okay, for that, you should use the reference of the iron and carbide equilibrium diagram for that steel. Okay, this is the iron and carbide equilibrium diagram. I have taken the half portion just for the reference, means for just steel. I have taken the iron and carbide equilibrium diagram for steel. Okay, starting from carbon percentage 0.008 to 2%. Okay, this particular point 0.8% carbon. This will be eutectoid steel point. Now this diagram will be very helpful. Means for throughout this chapter, you have to keep the iron carbide equilibrium diagram with you. Just draw that diagram on one paper or in your notebook, and keep it with you for your reference. Okay, each time whenever I am telling you the temperature range, then microstructures, phases, at that time that diagram should be in front of you. Okay, please keep that diagram with you. Then, for a better understanding of this heat treatment of the steels, first you should understand that there are some transformation products. Now, I will, in short, I will explain. Uh, in last lecture, we have seen the different steps in the heat treatment process. In that first step is the heating cycle. We are heating it, okay, and we are obtaining a homogeneous phase. Okay, homogeneous phase with the homogeneous structure, and we are obtaining, generally we are getting the austenite phase. Okay, uh, for that, and after getting austenite phase, we are holding at the that particular temperature, and then we are doing the cooling. Then means we are doing the cooling from that austenite phase, means this austenite will give you different products, or this austenite will get transformed, and depending on the cooling rate used, this austenite will get transformed in the different phases or different structures. Okay, it will give you different structures. Then which product is obtained with the, means which type of cooling rate you have to use to get which type of the transformation product, and what kind of properties are that product is having, and depending on that properties of that particular product at the end or at the room temperature, there depending on that properties only you can decide its application. Okay, for that, this part means this transformation product of austenite, this part is not included in your syllabus, but for better understanding of the all heat treatment processes which we are going to conduct, or which we are going to study, for understanding that processes you should understand the different transformation products of the austenite. Okay, depending on the cooling rate used, austenite will get transformed in the different kinds of the products. Generally, as here indicated in this diagram, austenite may get transformed in the pearlite, or it may get transformed in the bainite, or it may get transformed in the martensite, depending on the cooling rate used. Okay, depending on the cooling rate used, and depending on the temperature of the transformation. Okay, depending on the temperature also, depending on the temperature of transformation also, different products may be there, and generally only these three kinds of products will be there: pearlite, bainite, and martensite. Now here, first we are going to discuss how this austenite will get transformed to pearlite, and how this austenite will get transformed to bainite, and how it will get transformed to martensite. Okay, first try to understand the temperature zone. From this temperature zone, here austenite is there. Okay, the first cycle will be our heating cycle. We are heating it in the above this temperature. Either we are going to heat it above A1 or above A3 or above ACM. Okay, here austenite phase will be there, here also austenite is there, here also austenite is there, and here also austenite is there. And from this temperature zone we are transforming that, but particularly in this range we are having homogeneous austenite. Okay, above A3 and above ACM, homogeneous austenite will be there. After giving this sufficient holding time or soaking time, we will get the homogeneous austenite, and from this we are going to cool it. Okay, now depending on our cooling rate we will either get perlite, bainite, or martensite. Then how this austenite is getting transformed in these three different phases, that we are going to discuss one by one. The first one will be, first transformation product of austenite will be pearlite. Austenite will get transformed to pearlite, and some proeutectoid phases. Proeutectoid phase means the phase which are getting separated before this actual eutectoid transformation at this particular temperature range at 723 degrees Celsius. Okay, this horizontal line you can see here, this temperature line will indicate the eutectoid transformation temperature. Okay, and phases which are separated before this temperature range is before this 723 degrees Celsius. Suppose here you will get ferrite. Okay, ferrite, and here you will get the cementite, Fe3C. Okay, that will be termed as the proeutectoid phases. Proeutectoid phases, proeutectoid alpha, you can say that, or proeutectoid ferrite, and proeutectoid cementite. These are proeutectoid phases. Before actual eutectoid transformation, these phases will get separated during the cooling process. That's why it is termed as a proeutectoid phase. And this perlite is nothing but a mixture of ferrite alpha plus cementite. Okay, perlite is nothing but a mixture of ferrite and cementite alpha plus Fe3C. It is known as the perlite. Again, this bainite is also mixture of ferrite and cementite only. Okay, perlite and bainite, their composition will be same, but just their morphology or their appearance will be different. Okay, you have to remember this point, that is perlite and bainite. These two are nothing but the mixture of ferrite and cementite. Only their morphology or their structure will be different. And this martensite is having different structure. How it is formed, that we are going to discuss one by one. Okay, first you have to remember that depending on the transformation temperature and depending on the cooling rates used, austenite may get transformed in the perlite or bainite, or it will end up with the martensite. Okay, if you have used now, some cooling rates are there. If you have used the so slow cooling, if cooling rate is very slow, then you will get the perlite. If cooling rate is a little bit moderate or higher than that slow cooling rate, then you will end up with the bainite. And if you are doing the cooling with the faster rate, you will end up with the martensite. Now these cooling rates will depend on the type of the steel you are using, and depending on their compositions, it may get changed. Now, first, we will discuss how the austenite is getting transformed in the pearlite. That will be our next slide. That is transformation of austenite to the pearlite. Okay, before this, just I will give you 1 minute here. Please draw this chart. Means show the austenite, then different cooling rates, and show these three transformation products of austenite. Please draw it and put in the chat box that you have completed it. Just half minute or 1 minute will be required. It will take. Complete it and put that in the chat box. I will start the next point. Just draw the chart of transformation products of the austenite. Show the different cooling rates and three different products. You don't get in that microstructures that are not visible or not clear. That clear pictures I will show you in the next lectures. If you have completed the drawing of this chart, let me know. Okay. This one, okay. Austenite is having FCC crystal structure. Okay, here austenite is the interstitial solid solution of carbon in the gamma ion, and it is having FCC face centered cubic crystal structure. Okay, if you are having query, that also you can put in the chat box. Okay, fine. Okay, then next point, I will move towards the next point. It's first transformation product. That is austenite is getting transformed to the pearlite. Then how it is occurring? Now keep this diagram in your mind that we are austenite is transforming from this temperature zone. Okay, from your iron carbide diagram, from this zone we are transforming this austenite with different cooling rates, and we are getting these three products. Now what exactly is happening during the cooling process? Okay, first we will see with the what exactly happens when we are using the slow cooling rate. Okay, now the first whenever cooling rate is very slow, then austenite will get transformed to the pearlite. Now pearlite pearlite is the mixture of ferrite and cementite. Ferrite means your alpha. Okay, it is indicated here by the alpha. Here you can see that this is the ferrite, or you can say that alpha ion, interstitial solid solution of carbon with the alpha ion. That is that will be your ferrite. And this pearlite is mixture of ferrite plus cementite. Cementite means Fe3C. Okay, and now this pearlite is having the means this alpha ferrite or simply ferrite and cementite. It will be arranged in this manner. Okay, if you see the crystal structure, or under if you observe the pearlite under the microscope, you will able to see the alternate layers. Okay, in this way layered structure, layered morphology will be there. Means alternately ferrite and cementite will be there. Alternate layers of ferrite cementite, like this alternate layers will be there. Okay, this will be the final structure. This is the final structure, alternate layers of the ferrite and cementite. But how it is formed? It will start with the means in different stages. It had shown in the diagram. These 5 stages are there. All these diagrams I have collected from VD Code Garage book. Okay, you can refer that book for this. Now here, how this transformation means actually how the conversion of austenite into pearlite will occur. Now the first step will be nucleation. First step is here is the nucleation. And then how this nucleation will start? Whichever this line you hear, okay, this curved portion is here. This is the grain boundary of the austenite. Okay, we are cooling it from the, or we are doing the cooling from austenite phase. First, we have done the heating and we have obtained the homogeneous austenite by giving the sufficient holding or soaking time. And now we are going to do the cooling process. Now we have started the slow cooling. Now, while happening of this cooling, what will happen on this grain boundary? Okay, this line is the grain boundary of the austenite. On this grain boundary of the austenite, as temperature is falling, okay, as temperature is falling, carbon from this austenite will start diffusing on the grain boundaries. Okay, carbon will start diffusing in the form of cementite. Okay, carbon from austenite it will start diffusing on the grain boundaries of the austenite, okay, in the form of cementite. This is the cementite nucleus, Fe3C nucleus, and it grows age wise, okay, in this direction horizontally. It will grow horizontally, and now this cementite grows with the diffusion of the carbon. Okay, here in this diagram you can see that this is the cementite. This is the cementite austenite grain boundary. This portion is the cementite, and this is the ferrite. This cementite first initially nucleus will be formed, and this nucleus will grow. This dark portion, black dark portion here, it will grow by diffusion of the carbon. Okay, it will grow by the diffusion of the carbon. Carbon, from where you are getting the carbon? Carbon from austenite will get diffused here on the boundaries, and this cementite will grow with the diffusion of the carbon. And on the adjacent side, okay, on the adjacent side of this cementite will grow, and on adjacent side carbon deficient region will be formed. Okay, on the adjacent side carbon deficient region will be there, and due to deficiency of the carbon, this remaining portion will get transformed to the ferrite. Okay, in this way cementite and, okay, this is the cementite and this is the ferrite. The cementite is formed due to the diffusion of the carbon, and in the adjacent side to the cementite, some carbon deficient region will be formed, and due to this carbon deficiency, here ferrite will start growing. Okay, in this way cementite and ferrite alternate layers will be formed, and it will grow like this. It will grow, and number of alternate layers. Okay, as here cementite is formed by diffusion, here carbon diffusion will occur at the cementite, and alternate ferrite will be formed. Then as here carbon is less, uh, adjacent to this ferrite, there again carbon diffusion will occur, and adjacent to that ferrite cementite will form. In this way this process will get repeated again and again, and number of alternate layers of ferrite and cementites will be formed. Cementite is forming due to the diffusion of the carbon, and ferrite is forming due to the rejection of the carbon. Due to rejection, or in short you can say that in the carbon deficient region adjacent to the cementite, ferrite will get formed. In this way alternate layers of cementite and ferrite, this dark layer is cementite, then ferrite, cementite, ferrite, like this number of layers will be formed in this way: ferrite, cementite, ferrite, cementite. Okay, cementite is forming due to diffusion. Here diffusion will occur in the adjacent region due to the rejection of the carbon or deficiency of the carbon. Ferrite will form. The same way this process will get repeated again and again, and a large region having alternate layers of ferrite and cementite will be formed, and that region is termed as the colony. Okay, it will be termed as the colony. Here I have also mentioned the colony of the pearlite. This mixture or these alternate layers will be termed as the pearlite, or it is also known as pearlite colonies. Okay, and in this same way number of pearlite colonies will be formed. Some will be having this kind of morphology or appearance, some will be horizontal, some will be inclined. Like this number of layers will be formed, alternate layers will be there of ferrite and cementite. These are termed as the pearlite colonies. Okay, or simply you can say that this is the pearlite. In this way the austenite will get transformed to the pearlite whenever you are using this low cooling rate, and whenever you are doing the slow cooling rate. And here very important point is that this austenite is transforming to the pearlite due to the diffusion of the carbon. Okay, this is the occurring due to the diffusion of the carbon, and it will start with the nucleation of cementite on the grain boundary of the austenite. Then this nucleus of cementite will go age wise, it will grow age wise, and adjacent region ferrite will be formed, and they will grow together, cementite and ferrite. And In the same way, number of layers of ferrite and cementite will be formed. Togetherly, this number of layers of ferrite and cementite will be forming a colony of pearlite, and number of colonies will come together, and the whole structure of that pearlite is formed. Okay, in this way, the formation of the pearlite will take place. First, nucleation will occur, and after that, nucleation of cementite will occur, and after that, its growth will take place. Okay, which point you have to remember here? The cooling rate, slow cooling rate. Then how it is starting with the diffusion of the carbon and with the nucleation of the cementite. Okay, in this way, we are getting the pearlite here. Now, whenever we are having the temperature transformation temperature above 550 degrees Celsius, above 550 degrees Celsius, from austenitizing temperature, means from 900 or 950 degrees Celsius temperature zone, up to 550 degrees Celsius temperature. If you are cooling from that temperature zone, you will end up with the pearlite only. But whenever you are transforming the austenite below, means below 550 degrees Celsius, its morphology is different. Okay, instead of getting this type of structure, you will get the different morphology. Here we are having alternate layers of ferrite and cementite. Now this ferrite and cementite appearance will get changed whenever you are transforming the austenite below 550 degrees Celsius. It will change its morphology. Either you will end up with the feathery structure, or either you will end up with the needle shaped structure or needle shaped morphology will be there. And that phase is initially studied by scientist Bain, and he invented or he discovered that phase. That's why that phase or that product of transformation of austenite will be termed as the Bainite. Okay, that is the next product, transformation of austenite to Bainite. And before see how this transformation is occurring, how or what are the properties of these Bainites, before that, please draw these two diagrams. In the first diagram, growth of the pearlite in the austenite. Here the growth is shown. This is the grain boundary of the austenite. This is the cementite and ferrite, alternate layers of the cementite and ferrite. At this point, diffusion of the carbon will occur. Okay, here diffusion will occur, and at diffusion will occur here, and ferrite will reject the carbon and cementite will accept the carbon. Okay, and age wise, this colony will grow age wise in this direction. They will grow. Please draw the diagram and put that in the chat box after completing the diagram. And if you are having any query related to this transformation process, you can put that also in the chat box. Please draw the diagrams and steps involved in the nucleation and growth of the pearlite, or transformation of austenite into the pearlite. Okay, I will wait for 1 minute here. Please complete the diagram. Two diagrams, separate diagrams, and in the second diagram, you have to mention different phases. Okay, different phases will be there. You can give numbering for that phases. complete the drawing, first draw the grain boundary of the austenite, then draw this nucleus of the cementite, then grow the nucleus of cementite will grow, and towards to in the adjacent region to that cementite, ferrite will grow by rejecting the carbon, cementite will grow by accepting that carbon. Okay, age wise this will grow in this direction. Okay, this arrow is showing the growth direction. In this direction it is growing. Okay, initially nucleus will be formed, and in this direction these are growing. Okay, in this way number of layers of ferrite and cementite will be formed. Number of layers togetherly will be termed as colony of that pearlite, and number of colonies will come together to form whole pearlite region. Let me know whether we have finished the drawing, and if you are having any query, you can ask me. Put that in the chat box, I will try to clear it. Okay, after completing, put your reply that you have completed. Only few students are replying me, only few. Okay, after the first transformation product, that is austenite will get transformed to the pearlite whenever you are using the slow cooling. Okay, and this transformation will occur with the nucleation of the cementite. It will start with the nucleation of the cementite, and due to the carbon diffusion it will occur. Okay, now the second transformation product of austenite is the bainite. Now austenite will get transformed whenever transformation temperature we are using is below 550 degrees Celsius. Then this austenite will get transformed to bainite. Again, here bainite and pearlite, these are having these are nothing but the mixtures of ferrite and cementite. That is alpha plus Fe3C. Both will having this same composition, alpha plus Fe3C only, but their appearance or morphology will be different. Okay, in case of pearlite, you will see that their morphology, or when you are observing their microstructure, you will find that alternate layers of ferrite and cementite will be there. And when you observe the microstructure of the bainite, then you will find the needle like structure or feather like structure will be there. Then now how this austenite is transforming to the bainite, whenever your transformation temperature is less than 550 degrees Celsius, and whenever you are using the moderate cooling rate, at that time you will end up with the bainite structure at the room temperature. Then here it will also start with the nucleation. Okay, initial stage will be nucleation, but as we have discussed earlier here, austenite is transformed to pearlite, and pearlite transformation will start with the nucleation of the cementite. But this transformation of bainite, it will start with nucleation, will it will start with the nucleation only, but nucleation of the ferrite will occur here. Okay, nucleation of the ferrite. Why nucleation of the ferrite is here? Because we are using the lesser transformation temperature, less than 550 degrees Celsius. Okay, that for that we will refer this diagram. Okay, transformation temperature will be somewhere here in this region. Okay, from here we are transforming it. From this temperature zone, we are cooling it. From this temperature zone, below this, below 723 degrees Celsius, somewhere here. Okay, from this temperature zone, we are cooling it. We are cooling it. Depending on its composition, austenite will be there, but the actual cooling we are doing from this temperature zone. Then it will start with the nucleation of the ferrite, and here this nucleus is having faster growth as compared to previous phase. Okay, in the previous structure, here cementite and ferrite are growing simultaneously, they are growing and alternate layers are formed. But here in this case, the rate of nucleation is faster as compared to growth of that cementite, which is forming in the alternate regions, okay, or in the adjacent region. Initially nucleus of ferrite will be formed and it will grow, and in the adjacent region cementite will be there, but nucleation rate will be very high. Okay, in this way nucleation means ferrite will grow and one needle like structure will be formed. Okay, in this way you will see, you can able to see the needle like structure when you observe it under the microscope. Needle like structure or some feather like structure will be there, and it consists of ferrite, and this dark portion is nothing but the cementite. In this way, whenever transformation is occurring at the lower temperatures, then you will end up with the mixture of alpha, that is the ferrite, plus cementite, that is Fe3C, but it will be having different morphology. Pearlite is having layer type morphology and bainite is having needle shape or feather like structure. Okay, this is the difference between the bainite and pearlite. And this bainite, whenever the bainite which is obtained at the upper temperature zone, means near to the 550 degrees Celsius, that bainite will be termed as the upper bainite. Okay, the bainite which is obtained at the higher temperature zones nearer to the 550 degrees Celsius, it is termed as the upper bainite. And bainite which is obtained at the lower temperature zones, it will be termed at the lower bainite. Upper bainite will be having feather shape structure, okay, feather like structure, and lower bainite will show you exact needle shape structure, which structure I have shown here. Exact needle shape structure will be there in the lower bainite. And when you compare the upper bainite and lower bainite, okay, when you compare upper bainite and lower bainite, lower bainite is having higher hardness and higher strength. Okay, hardness will be there, it will be stronger, tougher, and harder in nature. It will be stronger, tougher, and harder in nature as compared to the upper bainite. Now when you compare pearlite and bainite, in comparison, pearlite will be softer as compared to the bainite. Bainite will be more hard. And in that bainite, upper bainite and lower bainite, two types of bainites will be there. In that, lower bainite will be having more hardness. Lower bainite will be having more hardness. In this way, austenite will get transformed to the bainite, and this transformation of starts with the nucleation of the ferrite. Nucleation of the ferrite, it will due to nucleation of ferrite, the austenite will get transformed to the bainite. And this process, nucleation of the ferrite and its growth along with the cementite, but growth of that ferrite nucleus is the faster and it will end up with the needle like structure with cementite in inside region. It will be termed as this will be termed as Bainite colonies, and number of Bainite colonies will come together to form that whole Bainite structure, and this whole model will be termed as Hultgren's model. Okay, in bracket I have mentioned it. Sometimes it may asked in some competitive examination. Okay, this is termed as the Hultgren's model. Then please draw this diagram. Transformation of austenite to the bainite. Please draw this diagram. This is the ferrite, nucleus of ferrite, and this darker portion is the cementite. Please draw the diagram, and after completing, put that in the chat box that you have completed the diagram. Then we will move towards the next transformation product, that is austenite is transforming to the martensite. Okay, please give proper naming. This is the ferrite nucleus. It will grow, and in the adjacent region, cementite will grow, but the nucleation of the ferrite will occur at the faster rate, and needle-like structure will be formed. Okay, this is the ferrite, and this dark portions will be of cementite. Okay, if you have completed the drawing, I will move towards the next slide. The next transformation product of austenite is the martensite. Okay, that austenite will get transformed to the martensite. Now, whichever products we have studied up to till now, that austenite is transforming to the pearlite and austenite is transforming to the bainite. These pearlite and bainite, these are formed due to the diffusion of carbon. Okay, some diffusion process of carbon is occurring there. Okay, sometimes diffusion will occur, sometimes rejection of the carbon will occur, but This Martensite transformation is occurring due to the shear mechanism. Okay, here you can say that there is no diffusion is involved here due to the shear mechanism. Whenever we are doing very faster cooling, whenever we are using the faster cooling rates, then cooling is done at a very faster rate. Then instead of formation of pearlite and bainite, that austenite will end up with giving the martensite product. This martensite is nothing but, it is nothing but the, you can say that it is a solid solution only, solid solution of carbon in the bcc alpha. Okay, you can say that bcc ion, that is your alpha ion. This martensite is nothing but the solid solution of carbon in the alpha ion. That alpha ion is having bcc crystal structure. Okay, this outer portion, just forget this inside portion. Okay, which you are having this dark spots, you forget this inside portion, just concentrate on this light colored part. Okay, this is the bcc crystal structure. bcc alpha ion will be there, and in that some, they will form the solid solution with the alpha ion. And here, while forming the solid solution of that, means whenever that carbon is forming the solid solution with the alpha ion, it exceeds its solubility limit, means it forms the supersaturated solid solution. The carbon will form the supersaturated solid solution with the alpha ion, and due to this, what will happen? This bcc, yeah, just here we are having two bcc structures, body centered cubic. Okay, just concentrate on this cubic structure with the lighter color. Okay, bcc crystal structure. Okay, just bcc crystal structure is there, two bcc crystal structures are there, and it will get compressed. Okay, it will get compressed vertical. Okay, here this vertical axis, please concentrate on the movement of this cursor. This vertical axis will get compressed, it will get compressed. Okay, from starting, this total axis will get compressed and it will become smaller. Okay, it will become smaller. And these horizontal axes are there, they will become equal. They will become, horizontal axis will become equal and vertical axis will get compressed. This structure formed will be termed as bct structure, body center tetragonal structure. body central Body center tetragonal structure, that martensite is having bct crystal structure. Okay, and how it is formed? Due to the shear mechanism. Due to the shear mechanism, what will happen here? During the shear, the vertical axis will get contracted and horizontal axis, two horizontal axes are there, they will extend, slightly extended, or they will adjust in such a way that the horizontal axis becomes equal in size, and they will form the BCT crystal structure, body center tetragonal. Martensite is having this inside structure. Okay, this inside structure with this dark bubbles. These are body center tetragonals. Body center tetragonals. BCT crystal structure. Vertical axis will get compressed or shortened, and horizontal axis, these two horizontal axes, they will become equal. This size will be equal to this size. In this way, this martensite is nothing but a supersaturated solution. It is a solid solution but supersaturated, means it exceeds the solubility limit. Supersaturated solid solution of carbon in the alpha ion, and this is formed due to the, you can say that the shear mechanism. No diffusion is occurring here, diffusionless transformation. This is diffusionless transformation. During the shear mechanism, vertical axis will get compressed, this vertical axis will get compressed, and horizontal, these two horizontal axes will become equal in size, In this way, the center structure, this is BCT structure, body center tetragonal structure will be formed. Okay, in this way austenite is transformed to the martensite whenever you are using the very high cooling rate, or you are doing the cooling very faster, or cooling rate is very fast, you will end up with, that is the austenite will get transformed to the martensite due to the shear mechanism. Okay, now here this martensite is having certain properties. Okay, martensite is having certain properties here, that we will discuss here, that is the effect of carbon content on the hardness of the martensite. In the depending on the type of the carbon, whenever low carbon steels, medium carbon steels, or high carbon steels are there, depending on the percentage of the carbon, they will having different hardness. Whenever high amount of carbon is there, okay, high amount of carbon is there, then its hardness values are very high. And why this portion is dotted here, this portion I have shown dotted, and this is the low carbon steels. In the plain carbon steel, it is the low carbon steel, carbon percentage is less than 0.3%. Then here it is almost impossible to do the cooling. Here to get the martensite, we required very fast cooling rate, and it is not obtainable in practical life. We cannot obtain that faster cooling rate, we are not having that sources available. So that's why these low carbon steels are non hardenable. Okay, in that type of the plain carbon steel, or in the classification I have told you that that plain carbon steels are classified in low carbon, medium carbon, and high carbon steels, and these low carbon steels are termed as the non hardenable steels. Then why it is termed as non hardenable, we are not able to obtain, or we are not able to get that cooling cycle so that it will form the martensite at the room temperature. It is almost impossible to achieve that cooling rate and to transform that austenite into martensite in case of that low carbon steel. Hence, these are termed as the non-hardenable steels. Okay, that's why it is shown in the dotted form. These are non-hardenable steels. Medium carbon steels, you can do the hardening also, and it will give you the more hardness also. Okay, then here in this diagram, here some what it is indicating, it is indicating the just what it has indicating here, austenite we are transforming to the martensite. The temperature at which martensite transformation starts, okay, please listen it carefully, these terms we are going to use in the TTT diagram and CCT diagrams. Temperature at which martensite transformation starts, that temperature is termed as the ms temperature, and temperature at which martensite transformation completes, that temperature will be termed as the martensite finish temperature, that is mf temperature. These terms will be there in case of pearlite and bainite also. In case of pearlite, it will be ps and pf. Pearlite transformation starts and pearlite transformation finishes. In case of Bainite, it will be BS and BF. BS means Bainite transformation starts, and BF means Bainite transformation finishes. Okay, in this way, different terms will be there. That terms will be very helpful in the TTT diagram. Now here, at different temperature ranges, at this temperature and this much time, 25% martensite, 50% martensite, 75% martensite will be there. Okay, in this temperature zone, at different temperature ranges, whenever you are doing the cooling at different time interval and different temperature zones, percentage of martensite will be different. Here 25% martensite will be there, and sometimes at the end, means at the room temperature also, or sometime to get the martensite you have to cool it below room temperature also, to get the martensite crystal structure. Depending on the carbon percentage only, it will vary. This ms temperature and mf temperature, ms temperature and mf temperature, generally gap in between these two temperature is 150 degrees celsius to 215 degrees celsius gap will be there in the ms value and mf value. 150 degrees celsius or 215 degrees celsius temperature gap will be there, and these values depends on the percentage of the carbon. And how these are dependent on the percentage of carbon, it is indicated in this diagram. In this diagram, ms temperature and mf temperature, as carbon percentage goes on increasing, okay, carbon percentage goes on increasing, this ms temperature and mf temperature will fall, will fall. And at this particular point, this is 0.7% carbon, 0.7% carbon steel, this emf temperature is near or equal to the room temperature. And whenever you are having higher carbon percentage than this zero point 0.7, this emf temperature, you have to go below room temperature also to get the complete Martensite, or to finish the Martensite transformation. You have to use the lesser temperatures than the room temperature. And sometimes you will not able to end up with, or in the most of the cases, you are not going to, or you are not able to transform whichever austenite is there. This austenite, this 100% austenite is not transformed to 100% martensite. Some amount of austenite is still there at the room temperatures, or at the end of the process. You will not end up with the 100% martensite. Some austenite will be there in the microstructure at the room temperature, and that austenite which is present at the room temperature also, it will be termed as a retained austenite or untransformed austenite. Retained austenite or untransformed austenite. And it can be transformed to the martensite by using different heat treatment processes that we are going to see in the detail. But in some cases we are not able to get the 100% marten. This 100% austenite is not transformed to 100% martensite. Some austenite will be there at the room temperatures also. That austenite will be termed as untransformed or a retained austenite. Then here this Martensite, whichever Martensite we are getting at the room temperatures or below room temperature, in some cases this Martensite will be having different types. Okay, depending on the carbon percentage only, we are having different types of the Martensites, as I have mentioned here: lath Martensite, mixed Martensite, and plate Martensite. Whenever we are having low carbon steels are there, low carbon steels we will get, or up to medium carbon steel, that is 0.6 percentage, we will get the lath martensite. The lath martensite will be there. This lath martensite, whenever you observe the microstructure, whenever you observe the microstructure, you will see the strip like structure or rod like structure there. That's why it is termed as the lath martensite, lath martensite. And whenever carbon percentage is very high, above 1%, you will able to see the needle like structure. A needle like structure will be there. Then this martensite will be plate martensite. And in between this region, 0.6 to 1%, combination of that rod like structure and needle like structure will be there. And that martensite will be termed as the mixed martensite. Depending on the percentage of the carbon only, different martensite appearance will be there. And depending on that, these are classified in lath martensite, mixed martensite, and plate martensite. Okay, so in this way transformation of austenite to the martensite will occur. Okay, this is the short summary at the end. This is the short summary. This austenite at different cooling rates, you will get the Pearlite, Bainite, and Martensite. Okay, sometimes there is one type tempered Martensite. What is the tempered Martensite? This Martensite is having, whichever obtained due to the very fast cooling, it is having very high hardness. Then some preheating or a reheating, sorry, reheating is done, not preheating, this is the reheating process. Means after getting that martensite structure, again it is heated above 200, or in the temperature zone of 200 degrees Celsius to 500 degrees Celsius temperature zone, and again it is cooled to make it little bit soft. That will be termed as the tempered martensite. Okay. Now, what related to their properties? Here I have written these all phases. Okay. Starting this, this will be at the end. At the bottom, austenite will be there. Then this pearlite will be having coarse pearlite and fine pearlite. Then bainite, upper bainite and lower bainite. Then tempered martensite and martensite. In this way, you have to write it. Then why we are writing in such a way? Because when you move from this bottom to top, strength will be higher, hardness and strength will be more. In short, when you compare austenite, I will tell you the sequence: austenite, then pearlite. In that pearlite, coarse pearlite and fine pearlite will be there. Then bainite. In that bainite, upper bainite and lower bainite will be there. And after that, martensite will be there. And in that martensite, tempered martensite and simple martensite, you can consider it as a martensite will be there. This austenite phase, austenite will be softer. Then after austenite, due to slow cooling, whichever product we are getting, pearlite will be little hard. Then with more faster cooling, bainite we are getting. Then bainite is more harder and stronger than the pearlite. And in this bainite, upper bainite and lower bainite is there. And in that, lower bainite is more harder and stronger due to the fine structure, due to the fine arrangement of the ferrite and cementite. Lower bainite is the more harder in nature due to the needle shape structure. It will be arranged finely or more compactly arranged. Then martensite. This martensite will be having highest hardness. Austenite will be softer. Then pearlite will be more harder than that austenite. Bainite will be more harder than this pearlite. Then martensite will be more harder and stronger than this bainite. Okay. And in this pearlite, coarse pearlite and fine pearlites will be there, depending on their grain size. This fine pearlite will be harder and stronger. In between these two, coarse pearlite and fine pearlite will be stronger and harder. Then in bainite, upper bainite and lower bainite will be stronger. Then this martensite and temper martensite, this martensite will be harder and stronger. Okay. Why we have, you have to remember this chart, this austenite, its different transformation products and their properties. Okay. Then whenever you want to improve the hardness, strength, cutting ability, then you have to get these phases. Okay. These phases are desirable. Means martensite is desirable when you want the more hardness. And suppose if you want the more ductility, or you want to increase the toughness, you should end up with the pearlite. Okay. If you want more hardness, then on this austenite you have to transform to the martensite. If you want more ductility or more better machinability or softness, then this austenite should be transformed to the pearlite. Okay. If you want the combination of means strength and ductility, then you have to use this moderate cooling rates. Means depending on the desired properties, you have to transform this, whichever properties you needed, that properties will depend on the structure. Then you have to change that basic crystal structure, that structure you have to change, and or that phases you have to change. And if you able to change the phase, automatically properties will get changed. In this way, we are doing the heat treatment process by using with the help of this transformation products. And depending on these cooling rates, you will be able to select the different cooling rates to get the desired phases and to change the properties according to our need. Okay. In this way, this is very helpful. These transformation products are very helpful. Depending on that only, you can select the cooling rates. And next point in this is the time temperature transformation diagram or TTT diagram. Okay, and this part is in your syllabus compulsory. One question will be there on this TTT diagram. Okay, please draw this diagram. Compulsory one question will be there. Yeah, they will ask you to draw this diagram, draw the TTT diagram, and you have to explain this TTT diagram. Either they will ask you compulsory TTT diagram will be there. Sometimes they may ask you this CCT diagram also, continuous cooling transformation diagram. Yes, same diagram is there. Just what is the difference that I will tell you. Some little bit difference is there that I will tell you. Just try to draw this diagram. I will wait for a few minutes here. Please complete the drawing and put that in the chat box. Please draw the diagram and put that in the chat box that you have completed drawing TTT finished the drawing of TTT diagram. TTT diagram is time temperature transformation diagram. This TTT diagram is time temperature transformation diagram. Okay, as we have discussed earlier, that depending on the transformation temperature only, that austenite will give you three different products, that is pearlite, bainite, and martensite. And whichever the kinetics of that phase transformation is there, means at which particular temperature and at that which time or which time interval, which phases are there, that are indicated in this time temperature transformation diagram. Okay, this TTT diagram will indicate what it will indicate: the phases existing in the steel. This is only for this TTT diagram is for steel. Okay, this is for steel. It will indicate the phases existing here. Different phases are there. Different phases. This austenite, A for austenite, ferrite, cementite. Different phases are there at different temperatures and at different time. It will be indicated by this TTT diagram which indicates the phases existing in the steel at different temperatures and at different time. That diagram is termed as time temperature transformation diagram. In short, it is termed as TTT diagram. Whichever diagram is shown here, this is TTT diagram for eutectoid steel. Eutectoid steel means plain carbon steel with 0.8% carbon, exact 0.8% carbon. And whenever in plain carbon steel, carbon percentage is less than 0.8, it will be hypoeutectoid steel. And if carbon percentage is more than this 0.8% carbon, it will be hypereutectoid steel. Okay, this diagram is for eutectoid steel, exact 0.8% carbon steel. And in the next slide, I have shown here low carbon steel and for high carbon steel diagram. Okay, low carbon means less than 0.8, and particularly this diagram, I got this from the VD Code Gear's book. This is for 0.35% carbon steel. Okay, if you have written TTT diagram for hypoeutectoid steel, it is also sufficient. And this is for hypereutectoid steel, means carbon percentage is more than 0.8. And this exact diagram is for 1.1% carbon steel. If you write the hypereutectoid steel TTT diagram for hypereutectoid steel, it is also okay, no problem with that. Okay, just two different diagrams will be there. Then how this diagram is obtained, what the different symbols are indicating here, that I will explain. Okay, now first I will explain some different symbols here we have used. This A, this is the, this is not A, actually this is the temperature, A1 temperature. A1 temperature, okay. This is the A1 temperature. This 723 degrees Celsius temperature. This horizontal line, this is A1 temperature, A1, 723 degrees Celsius. Eutectoid transformation temperature. That is the horizontal line. Then this A is the austenite phase. Okay, A is austenite, then F is the ferrite, C is the cementite. Okay, then this PS and PF. Earlier I have discussed this. Pearlite, the temperature at which pearlite transformation starts, that temperature will be indicated by PS. Temperature at which pearlite transformation completes, it will be indicated by PF. Then same symbols are there for Bainite transformation start, it will be BS. For Bainite transformation finishes, it will be BF. Then Martensite transformation start, MS, and somewhere below this MF will be there. That is the Martensite transformation finishes. Okay. Then on the this right corner here, hardness is plotted. You will able to see that hardness is increasing when you move toward in the downward direction. That is, whenever you are getting the different products, for pearlite transfer hardness is lesser, by for bainite more hardness will be there, and for martensite highest hardness will be obtained. Now where this diagram is useful for you, depending, you here from you will get the idea that at which temperature conditions, for particular temperature conditions and time conditions, which phases will be there. Depending on that, you can select the cooling rate depending on the desired phases. Suppose you want Martensite, then you can select the desired cooling rate. If you want Bainite, then you can select the desired cooling rate. Like this diagram will be helpful for selecting the desired cooling cycle or proper cooling cycle to get the desired microstructure and desired properties. Okay, now how this TTT diagram is plotted or this is obtained, first I will explain it. In examination, you have to, if they have asked you just drawing, you have to draw this diagram, mention all the phases, temperature points and hardness values, and you have to mention here on the left side or whichever side is available on your paper, you have to indicate what these symbols meaning. You have to indicate the meaning of these symbols, whichever symbols you are used. Means A stands for austenite, F stands for ferrite, like this for each. A austenite, ferrite, cementite, then PS, PF, pearlite transformation start and pearlite transformation finish, like this for that Bainite also, BS, BF, Martensite, MS, MF. All these points you have to indicate. Okay, then how this diagram is obtained, this TTT diagram, how the practically this diagram is obtained. Some procedure you have to follow, some practical procedure is conducted there, and it will be like this. Some standard sized steel samples are taken, standard sized steel samples are taken, and all the steel samples are heated in a furnace up to austenitizing temperature, means above this time, above this temperature, and these steel samples are heated in a furnace. Okay, in a furnace these are heated, and equal soaking time is provided for all samples. Okay, to get the homogeneous austenite with uniform heating above austenitizing temperature, it is heated, homogeneous austenite is obtained, and sufficient soaking time is also provided for all sample. Number of samples are taken, and this procedure will be performed in a single furnace. Now after getting the homogeneous austenite by providing the sufficient soaking time, all these samples are collected and these are transformed to the second furnace. Okay, in a new furnace. Here in this furnace, first furnace, we have used the temperature above this A1 line. Okay, above this A1 or eutectoid transformation means above 723 degrees Celsius. Above A1 temperature means above this temperature we have taken number of steel samples and we have heated above this A1 temperature, and after giving the sufficient soaking time or holding time, we are collecting all these samples from this temperature zone and we are transforming in the next furnace, and in that furnace temperature will be less than this A1, less than this A1 and above this MS. In this temperature zone some temperature is selected, and at that particular constant temperature all samples are heat kept at that furnace in somewhere, some value is selected in this temperature zone between A1 to MS. Between A1 to MS heating is done above A1, and that is conducted in one furnace. All samples are collected and shifted in the next furnace or second furnace, and in that second furnace temperature will be between A1 to MS. And now from that second furnace we are now selecting one sample. Rand means in the, you can say that remove these samples one by one at a fixed interval of time. We are removing one by one sample at fixed interval of time, and we are cooling that in the water, in the brine solution or in the cold water. We are directly cooling it, and here we are observing whichever microstructure or whichever products we are getting from austenite, whichever products we are getting, that details we are collecting, and we are plotting it on a curve of temperature and time, and we will end up with this diagram. Okay, this type of curve will be obtained, and this process we are keeping that whichever all the samples we have kept in a furnace, and we have kept the temperature constant In this zone A1 to ms zone, we have kept the temperature constant, and at fixed interval of time we are removing one sample and cooling it in the water. That's why this is termed as isothermal transformation. Okay, this is also termed as isothermal transformation, and diagram obtained is termed as isothermal transformation diagram. This is also termed as TTT diagram, time temperature transformation diagram. And whichever curve is obtained, it is having C shape or S shape. That's why it is also termed as C curve or S curve. It is also termed as C curve or S curve. Now this is the diagram for eutectoid steel. And whenever hypoeutectoid steel is there, hypoeutectoid or hypereutectoid steel is there, this some changes it will shift towards, means it will shift towards this temperature zone. Okay, temperature point, this temperature line it will shift. Okay, in this way it will get shifted. For hypoeutectoid steel, curve will be shifted, and here A1 and A3 temperature zones will be there for hypereutectoid steel. And for hypoeutectoid you have to show A1 and A3, and for hyper A1 and ACM you have to show. You can take the reference of iron carbide equilibrium diagram. Just what you have to understand here, here in case of hypoeutectoid steel, martensite formation is very difficult. Okay, here martensite transformation is very difficult. You are getting very small gap here, or you have to do the cooling, which will be faster than this. Okay, here somewhere here curve you have to get faster cooling, less than 1 second. It is almost impossible. That's why hypoeutectoid steel we cannot do the hardening. But in case of hypereutectoid steel, you will be having more time or little bit time to get the martensite transformation of the martensite. Okay, just two diagrams will be there, just little bit changes will be there. That is A1 and A3 line is here in hypoeutectoid steel, and in case of hypereutectoid steel, A1 and ACM temperature line is there. Remaining curves are same, BS, BF, PS, PF, some phases are there that you have to indicate. Okay, some temperature in the phases only will be there, that you have to mention here. This is the time temperature transformation diagram for hypoeutectoid steel and hypereutectoid steel. Okay, then after this time temperature transformation diagram, one more thing, the, this node shaped structure. Okay, node shape in this curve, this particular temperature at the nose of this curve, this particular temperature exactly at this point is termed as the nose temperature. It is termed as the nose temperature. Okay, now why I am telling you this, this is the nose temperature. Please try to identify, see this cursor here. At this exact this point, at the nose of this curve, this temperature is the nose temperature. And whenever cooling rate which just touches this nose, that cooling rate will be termed as critical cooling rate. Okay, this is the nose, and the cooling rate which just touches this nose, it will be termed as critical cooling rate. Or in other word, you can say that the critical cooling rate is the rate at rate which just bypasses, it just bypasses the nose. This is the nose of this C curve, S curve or TTT curve. It just bypasses that. That's why it is termed as the critical cooling rate. Or in other words, you can say that this critical cooling rate is the rate which suppresses the diffusion, or you can say that pearlitic transformation. It suppresses the pearlitic transformation. It forms the martensite. It forms martensite. Pearlite transformation is avoided, or diffusion transformation is avoided. That is termed as the critical cooling rate. And this critical cooling rate depends on the percentage of the carbon as well as percentage of the alloying elements. Okay, as percentage of the carbon and alloying element, as percentage of the carbon and alloying element is more, this critical cooling rate will decrease. Okay, it depends on the percentage of alloying element and percentage of the carbon. Okay, that's why for cooling of the to get the martensite for low carbon steels, we have to do very faster cooling. We have to do the faster cooling, hence low carbon steels cannot be hardened. Okay, here some Pearlite and Bainite I have shown here: coarse Pearlite, fine Pearlite, upper Bainite, lower Bainite. Okay, coarse Pearlite is having, it is will be softer and less harder, less strength. This fine Pearlite will be little harder and stronger. Upper Bainite will be more harder and stronger, and this lower Bainite will be more harder and stronger as compared to all these three types. And at the end, you will get the Martensite, which will be having highest hardness. Okay, and in this studying this critical cooling rate, after studying this critical cooling rate, the next is the CCT diagram, continuous cooling transformation diagram. Okay, now here, what is the meaning of continuous cooling transformation diagram? When the steel is cooled continuously from higher temperature to the lower temperature. Okay, from higher temperature to the lower temperature, steel is cooled continuously. Okay, in the isothermal transformation or in the TTT diagram, what we have observed, we have kept the samples in the furnace at a particular temperature. That's why that, and we are taking one by one sample from that furnace and we are cooling it. But in case of this continuous cooling transformation, we are cooling the sample continuously. Continuously cooling is occurring, and randomly we are selecting one sample and dipping directly it into the water, and that curve obtained is the CCT curve. This darker curve is the TTT curve. Darker curve will be TTT, and this dotted portion curve remaining will be same. This dotted portion curve is the CCT curve, continuous cooling transformation curve. Okay, means whenever you are using the continuous cooling, this TTT curve will shifted towards right side and in the downward direction, towards right side and in the downward direction. This dotted curve will be TTT curve. This will be TTT curve. TTT curve shifts towards right hand side, downward, and after that it will overlap. Okay, remaining diagram will be same. This ms mf temperature, this a1 temperature will be there. This is the TTT curve. First, you have to draw the TTT curve, then CCT curve shown by this dotted line. This is the CCT curve. Now, I will explain how this continuous cooling transformation curve is obtained. The specimens are taken. That specimens are heated in the austenitic region. Number of specimens of steels are taken. Then that's samples are heated in the austenitic region and cooled with a constant cooling rate to some definite temperature. Now here we are doing the continuous cooling, and now randomly at the definite interval of time, one by one, we are selecting the samples and we are doing the cooling. And after cooling it, we are observing the microstructures, and whichever phases are there, we are plotting it by taking the temperature as a function of time, and we are obtaining a curve. Okay, in TTT diagram, temperature we have kept the constant, and in the CCT diagram, continuous cooling we are doing. Continuous cooling is there. Okay, that is the difference in the TTT and continuous cooling. That is time temperature transformation diagram. It is also termed as isothermal transformation diagram, because we have kept the temperature constant here, and here we are changing temperature continuously, or continuous cooling is happening. That's why this curve is termed as the continuous cooling transformation curve. Now here these curves are nothing but four different cooling rates I have taken here. This is the faster cooling rate. Then this is the cooling rate, which this is the critical cooling rate. It just touches the nose, or just bypasses the nose, or you can, in other word, you can say that it suppresses the diffusion transformation, or it avoids the pearlitic or bainitic transformation. Okay, just touches the nodes. This is the critical cooling rate. Then little bit two slow cooling rates I have taken here, and some values I have taken here, that is degree Celsius per second. That is, these are the different cooling rates. This is the faster cooling rate. Now I will explain it. Whenever faster cooling rate is there, you will end up with the Martensite. Okay, you will end up with the Martensite, and this Martensite will be having highest hardness. Then the next cooling rate, the second cooling rate, having 140 degrees Celsius per second rate. This is the critical cooling rate. This is the critical cooling rate. It avoids the nose of this CCT diagram, this continuous cooling transformation diagram. The next curve here, you will get, here also you will get the Martensite only. Okay, here also with this critical cooling rate, Martensite will be there. You will get the Martensite only. Then the third, in the third cooling rate, this third cooling rate, this cooling rate 35 degrees Celsius per second, in this cooling rate you will end up with the Pearlite. In both the 35 degrees Celsius per second and 5 degrees Celsius per second cooling rate, in both these cooling rates you will end up with the Pearlite. But when cooling is little bit faster, you will end up with the coarse Pearlite, and when cooling is little bit slower, you will end up with the fine Pearlite. You will end up with the fine Pearlite. Just you have to give the description related to this only. Means faster cooling rate, you will end up with Martensite. Then with the critical cooling rate, again you will end up with the Martensite. Just you are avoiding the diffusion transformation. Then when slower cooling rates are there, diffusion transformation will take place and Pearlite will be formed. And when cooling rate is faster, you will able to get the coarse Pearlite, and with slow cooling rates you will able to get the fine Pearlite. And in case of this continuous cooling transformation, here I have indicated this BSBF, but in actual practice we are not getting the Bainite phase in this diagram. Okay, that is the difference between CCT and TTT diagram. In TTT diagram and CCT diagram, this is the difference. In CCT diagram, we are not able to get the Bainite phase. We are not able to obtain the Bainite phase. Bainite phase is not obtained here. Okay, whenever steel try to enters in this region, Bainite transformation region, it's the Pearlite transformation will start. Pearlite transformation process will start. In this continuous cooling transformation diagram, CCT diagram, Bainite is not formed, and in TTT diagram, Pearlite, Bainite, and Martensite, depending on different cooling rates, can be obtained. But in CCT diagram, Martensite and Pearlite will be obtained. Bainite, we are not able to obtain the Bainite here in this diagram. That is the difference between CCT and TTT diagram, basic difference. Okay. First difference is related to the temperature. In the TTT diagram, temperature we have kept the constant. Here continuous, we are doing continuous cooling. Then whichever curve is obtained in the CCT diagram, it will shift towards right hand side and a little bit downward. And the next is, here in continuous cooling transformation, we are not able to get the Bainite phase. Only Pearlite and Martensite we are able to obtain here. And in TTT diagram, we can obtain Pearlite, Bainite, and Martensite. All three phases can be obtained here. Okay. In this way, this TTT diagram and CCT diagram we have studied. Now, in the examination, compulsory one question will be there. You have to draw this TTT diagram, or you have to draw the CCT diagram. Sometimes they have also asked the critical cooling rate. What is the meaning of critical cooling rate? Then you have to draw this diagram. This curve is same, just it is shortened. It is shortened. Or you can draw this same TTT diagram and just show the curve here, which touches this nodes. That is also sufficient. Okay, same diagram is there, just it is little bit zoomed. Okay, the critical cooling rate, it is the rate which just bypasses the nodes, or it suppresses the Pearlitic transformation or avoids the diffusion transformation, that is termed as critical cooling rate. and it depends on the percentage of carbon and alloying element. As percentage of carbon and alloying element increases, this critical cooling rate decreases. Okay, critical cooling rate decreases. Okay, in this lecture we have studied the transformation products of austenite. Three transformation products are there. Austenite may get transformed to pearlite, bainite, or martensite depending on the cooling rate used. If we have used the slow cooling rate, okay, this is the, if you have used the slow cooling rate, we will end up with the pearlite. If you have used the moderate cooling rate, we will end up with the bainite. And if we have used the faster cooling rate, we will end up with the martensite. This Martensite is having highest hardness, then Bainite, then Pearlite, and Austenite will be softer phase. Then after this, we have studied the, okay, after seeing this transformation products of Austenite, after seeing transformation of products of Austenite depending on the cooling rates, three transformation products and their different properties, then TTT diagram, time temperature transformation diagram, which is also known as C curve, S curve, depending on its shape, and isothermal transformation diagram or IT diagram, depending on the temperature zone which we have used. This is isothermal transformation TTT diagram because we have kept the temperature constant, and one by one we are selecting the sample for cooling. And in CCT diagram, continuous cooling is there, and randomly we are selecting one component and we are doing the cooling directly in the water, and air cooling is continuously occurring there. That's why it is termed as CCT diagram, and we will get the this CCT diagram. Okay, then different for different cooling rates, different phases we will get. Okay, that you have to explain here in the CCT diagram. And in TTT diagram we can obtain pearlite, bainite, and martensite, all three phases depending on the different cooling rates. But in CCT diagram, bainite transformation is not possible, only pearlite and martensite transformation is possible. Whenever we enter in this bainitic transformation zone, it initiates the pearlite transformation. Okay, and we will end up with the pearlite only. Okay, in this way we have studied the transformation products of the austenite, TTT diagram, CCT diagram, and critical cooling rate. Okay, if you have any query you can ask me. Please ask me if you are having any queries related to this TTT diagram, CCT diagram, critical cooling rate, or transformation products of austenite. Put that in the chat box. And if you are not having any query, I will stop here. I will stop here. Thank you for attending the lectures. I will stop here.